Hi, everyone. So my name is John. I'm with F5. Thank you for coming. I know this is the first session after a lunch. Typically, people get sleepy after lunch, but hopefully my session will be interesting that can keep you awake. So the topic today we wanted to share about to the community is about weighing options about with OpenStack and Kubernetes for AI delivery. And the reason we picked this topic was because this is an open source community, and so I guess the elephant in the room is that AI is the biggest modern deployment that has the least open source components. I hope that everyone would agree with you, because NVIDIA and a lot of proprietary technologies actually occupy the core of AI delivery. That's where the GPU lives, where the AI servers gets built, which is why we wanted to share some of our perspectives of how open source is helping and how it can still be relevant, open source still be relevant to AI delivery. And what are the options when we went through this process of helping some of our partners and customers building their AI, what was that thought process and what we got out of it that can help you to pick the right tools, use the right things to build AI infrastructure. So the topic today is about open source. It's about infrastructure for AI. Without further ado, let me dive into it. So we have basically three sections for today's topic. And I wanted to take you through each one of them. Some of them is background information that we got from our interactions with open source projects and also our customers. Some right from our own experience with running AI in our infrastructure. So let me get into the first one. So where are we at running GPU infrastructure, right? One of the key messages I wanted to share is that currently GPU infrastructure is mostly owned by the big names, NVIDIA's primarily NVIDIA, right? And so the tool chains and everything are very proprietary. And in terms of scale, we've heard about many newses about Meta, OpenAI, all of them are doing data center scale infrastructure, right? Open infrastructure is not something that they are using for this kind of a deployment. Well, there are tools that are adopted, but in most of these cases, a lot of the closed source proprietary designs and architecture software go into the structure. So that's the fact of the data center scale. And it's primarily relying on bare metals. And so the things that we do with OpenStack, with Kubernetes, may not be fully relevant in that scenario. And they have, even though they leverage a lot of open source tools, but that is not for our practice for enterprise use cases. But as we see that now that the LLMs are evolved at a stage where delivery of these languages has become quite sophisticated, and deploying for these solutions become important. So that we can see cluster scales and host scale AI deployments. This is what we're going to focus on today: cluster scale and host scale. Those are two kind of deployments, infrastructure deployments that are relevant to open source, more relevant to open source, and we are going to share what we learned along the way. So the reason that, as I mentioned, that cluster scale and host scale are becoming so important is because training has becoming kind of slowed down, and inferencing is the dominant use case now, and that's coupled with two things, right? There are two chains that we see in the industry. One is industrial models that are specific to a specific industry, let's say medical, autonomous driving. So these are the things that people train on large infrastructure, but run on small infrastructures that can be either on a single board or one or two GPU servers that can uphold the entire workload. So that's what brings us to the cluster scale, what brings us to the host scale. And the other thing is about the bottom that we can see there's quite a number of open source models. Some produced in Europe, some in China, some in the US, and basically these models can now be run on single servers, basically. And that also enables enterprises, small and medium-sized enterprises, to run these models on small infrastructure. And this gives us room, gives us the open source community the room to run these infrastructure with open source tool chains. And this is going to be what we are going to focus on today. And because of the chain that's said, I want to give an example of what we mean by host scale AI infrastructure. In the past, we used to see this, right? At the top left side is an NVIDIA network architecture for NVLink. This is the backbone of OpenAI training, of meta training, that delivers 100,000 GPU altogether in one infrastructure, right, for their LLM training. And this becomes, and it usually takes about months to finish these training cycles. And you have to sustain that training cycle with 99.9% of precision, success rate, right? Make sure that infrastructure can support a long period of time of running AI training workloads. So that becomes, that kind of is in the past. Now what we can see is that many of the private deployments and cloud deployments for AI has become much smaller, focused around like 4 GPUs and 8 GPUs. This can be a cloud deployment. You can rely on AWS, the public cloud hyperscalers. You can also rely on self-established hardware infrastructure, right? It's easy now to get a relatively medium level GPU infrastructure, let's say L40 from L40S from NVIDIA, and just run on any proprietary data center environment. And this is where the host scale becomes so interesting. This is also where we see in our experience that the open source community, especially the OpenInfra guys here, that we can contribute to, we can work on to support a better AI kind of infrastructure. And what do I mean by that, right? What do I mean by that? At the host scale, why is the host scale AI infrastructure so relevant to open source tools and open source ecosystem? You can see from the left-hand side, there's primarily, so this is the slide, this is a picture that I borrowed from NVIDIA, but it basically tells how NVIDIA sees this stack. This is the original stack from NVIDIA, where you can see, okay, they've defined NVIDIA certified system, NVIDIA's own GPU, virtualization, and virtual GPUs and compute drivers, right? So everything, the full stack, it's NVIDIA. It's proprietary, it's closed source. And people usually, when you are Facebook, when you are Google, when you are OpenAI, you can afford to have this. And because your target is to train a billion, trillions of parameters of the LLM system, right? A model. But when you are medium-sized enterprise, which is some of the customers that we talk to, or when you are regional cloud provider, let's say in India, there's Yotta, there's TCL, there's Tata. And then in Korea, we have Naver, we have Kakao, right? These are regional cloud providers. They also run AI infrastructure. And their target is not to train like a super high-end LLM that do not rely on this whole NVIDIA closed source stack. But instead, it's offering services to small-scale deployments of inference. And that gives us opportunity as an open source, open infra community to do more with the open source tool chains. So if you look at the right-hand side, I've laid out some options. And these are the real deployment examples that we see with a lot of the industry practitioners. NVIDIA is at the bottom, of course. The GPUs are from NVIDIA. But the systems are more open source based. People leverage Ubuntu and CentOS and all of that, as well as KVMs and KubeVirts to provide virtual machines management. And then on top, you can have GPUs pass through without subscribing to a virtual GPU infrastructure. The entire GPU can be offered to an upper layer application, upper layer VM to run the workload. So this is how these open source components can be key in terms of replacing or swapping out the proprietary options. And when we do that, what do we mean by open source in these infrastructure? I wanted to dive a little bit into this section. So the primary reason, as I said, a lot of our partners and our customers in enterprise side, they look into open source solutions to do these things, to run host scale AI inferencing. And there's three primary reasons for the community to do that. One is to drive down cost, right? I mean, NVIDIA is not cheap. The GPUs itself is not, it's very super expensive already. And you add on top the software stack that are proprietary and subscription-based, all of these. And even, let's say, there's VMware in the picture. VMware itself has become astronomically expensive because of the acquisition. So driving down cost is the key to this host scale because you simply don't need a lot of closed source software. So open source can become that single platform for many of the things here. And to maximize the use of the servers, right? So the servers and resources. In the past, you dedicated the hardware itself to a task of building or training LLMs for months on end. But these days, an infrastructure for the inference may only need it for a short period of time, a couple of days. In some cases, if you wanted to iterate through some models, try different models in different deployments, you may only need it for just a few hours to test out things, right? So it's a software, open source software, agile scale kind of deployment. And this gives us room to operate AI infrastructure like a cloud. And how to make sure that it's going to become a cloud, there's a few things that come into picture. That's one reason of doing this. And the second thing is reducing complexity. We all know that in the past, AI it used to be very complex to set up, the GPUs or the drivers and the libraries, right, from NVIDIA. And it basically dominates, and it's hard to configure. It's not using automation and tools from open source, right? The things that we are very used to, YAMLs and in past the Ansibles and Terraforms and things like that. And it's basically not in existence with the large-scale AI training infrastructure. So when we go to the host scale, it becomes important that we can adopt that. And the third thing is about security. Security is non-existing in training phase because you're in a closed data center infrastructure, and environment itself is closed. It's really hard to actually penetrate into such an infrastructure. But when it becomes host scale, when you're offering this to someone in an enterprise environment, to different departments, and people only use the resource, only use the GPU infrastructure for a short period of time. You have to switch context, and there are all kinds of people that can access this AI asset. It becomes a security issue. So that's the three main drivers of going into host scale. And we're going to have some data to prove that. But before we go to the data side, I just wanted to bring your attention to this slide. This is what we see today, how people are building different models of host scale AI infrastructure. On the left-hand side, of course, is things that we all are familiar with. We have OpenStack, right? We can use an OpenStack KVM. But underneath, of course, NVIDIA takes a large chunk of that hardware asset. But at the top, on the left-hand side is the hypervisor. People used to use the OpenStack and KVM to manage the infrastructure, right? It's how many GPUs available, how many servers available, what's the number of CPUs that I can use for this cluster, and how I can cluster together. And on top, they will use tools like VM, Kubernetes in the VMs, and doing pass-through of the GPUs, allowing the VMs to actually own the GPU completely for the lifecycle of the AI task. And this is a combination of Kubernetes on hypervisor VM, and OpenStack plays an important role in here, and GPU is in the pass-through mode to make sure the tenant Kubernetes owns this piece of infrastructure and owns it for a period of time that is allocated to it. So that's one way that we see Many of our partners are doing it. And second way is interesting also. It has to do with VM, but it's VM on containers. People are running Kubernetes inside a container VM, and the VM is laid on top of another Kubernetes infrastructure. This is similar to the left-hand side, but in this case, it's end-to-end Kubernetes. The virtualization is just a tool to enable that the hardware pass-through of the GPU onto the container Kubernetes, container VMs. Right, so this is the second method of people building this infrastructure of host-scale AI delivery. The third one is all very interesting to the open source communities and Kubernetes, pure Kubernetes-based infrastructure. And this is something that NVIDIA also supports a lot. In NVIDIA's use case, they usually have a bare metal deployment with Kubernetes. And so some of our partners and customers are also using virtual Kubernetes on top of Kubernetes. And this way, the hardware piece of the GPUs can directly be allocated to a virtual Kubernetes environment. But all of these has one problem, has one single problem, is how do we isolate? Because now we're talking about host scale. We're not talking about a single tenant, a single training infrastructure that runs a single task for several months. We're talking about 1 GPU, 4 GPU, and 8 GPUs at a host scale to run an inference for a short period of time. It could be a couple of days, it could be weeks, but that resource eventually will be released to somebody else. And it'll be shared amongst different users, because now we're talking AI in GPU, models in the GPU, APIs and applications on the CPU. And how do we make sure that this GPU resources would not spill over into the GPU? And somebody using 1 GPU, how do we make sure that this resource will not be violated or being penetrated by another tenant? So security is going to be key in this piece, and how do we solve it? The way that we, F5, the way that we see it, and the way that we practice it in the recent engagements with different deployment, is that NVIDIA may have provided an accelerated computing, right? This is what they always said. We are providing accelerated computing with the GPUs. But there's no accelerated operation, right? So the operation part is what we here at OpenInfra community, at open source community, we can provide with all the tools, all the open source components, right? This is one thing we can do. But it doesn't solve the other problem about networking. Networking here is still dependent on virtual switching, virtual routing at a hypervisor level. And so this is what I want to bring your attention to, is this second part, is the network stack evolving from the east-west chaining, super low latency, high throughput, end-to-end scale, NVLink, to something of an Ethernet for inference and rack at the host scale. That's the change in terms of networking. So people no longer rely on this super expensive east-west NVLink, but rather rely on an Ethernet network, TCP/IP-based network. And this is a network that people usually think it's vulnerable, it's easy to attack, you can adopt different tools, right? Layer different firewalls and security policies on top, but you still have to make sure that you have proper isolation, you have proper, so this is what we think in the picture of open source. There's a closed source infrastructure of accelerated computing, and we here at the open infrastructure community can leverage the open source tools to provide management of these technology. And then there's another piece of accelerated networking that can be done at a very important piece of hardware. It's called a DPU. And it solves a couple of things. First of all, it does provide tenancy. Tenancy at network level, at Kubernetes level, tenancy at compute level, right? Tenancy that can actually segregate different VMs, segregate different GPUs. That's the level of tenancy we're talking about. And second thing is it delivers security on top. So at the accelerated networking stack, it delivers security, And last thing, because this is the DPU, it removes the dependency of the CPU. It accelerates the traffic path for AI delivery. Remember that when we had this infrastructure, one of the key things that people has to use this east-west NVLink is because high speed, low latency. And so that when we go to this kind of host-based models, networking acceleration is still required for AI workload. And this is what we see as important. So I'm going to show an example, right? We set up a few labs with similar setup, with pure open source tools, and some accelerated networking components. And we're putting it in comparison, let you to see, okay, open source, we have a very good space in host scale AI delivery. But in some cases, we can still leverage some of these proprietary technologies to accelerate the stack. So we have 3 servers we set up in a lab, and just wanted to share with you and report to you what we observed in this kind of lab. So on the very right-hand side is the pure Kubernetes, right? It's a pure Kubernetes with a different CNI, which is the eBPF-enabled CNI. In the middle, there's a Kubernetes open source with a Calico CNI. This is a host. There's a full host without any acceleration, right? It's a basic, all of the basic open source tools, all the basic open source tools. And on the very left side is open source, but with some closed source components. One of the key things is the NVIDIA DPU, which is almost in every high-end NVIDIA GPU server. And the other one is the software from F5. So this is the only thing we swapped out in this setup comparison. And we got some very good interesting result for you to see. So this is the setup with some servers, exact configuration of those servers. And we have the DPUs inside all of the servers, but some of those are not enabled. They're just enabled so the infrastructure is exactly the same. They're just enabled as a NIC card. They're not enabled as a DPU. So there's only one being enabled as a DPU. And with this exact same setup, we're trying to deliver this, or arrive at this kind of a user scenario, yes, where you can have an infrastructure Kubernetes, you can have a virtual Kubernetes to run the actual AI workload dedicated to tenants. And we wanted to see separation of, first of all, performance, and second thing is security. And we demonstrated that with the setup, and what we got, it's something like this. And we wanted to share that. So this is one metrics we looked at. So with this kind of setup, we're using open source tools, a basic NVIDIA server, and if we compare these 3 kind of deployment models, native Kubernetes and accelerated networking with CNI, and then a DPU with B&K, which stands for Big IP for Kubernetes. From F5, this is an F5 solution, a software container. It can deploy on any Kubernetes infrastructure. It has compatibility with Kubernetes CRDs and gateway APIs. So you can simply view that as an open source component, right? It integrates nicely into Kubernetes. So when we deploy that, you can see in terms of capacity, this is measured by the number of API calls, right? Hitting this cluster. Number 1, with a native Kubernetes, we get about 3,000 TPS of API transaction per second. And with a CNI-based accelerated eBPF, we get about 18,000 of capacity for API request. And with the accelerated networking stack, it gets to about 100,000 TPS. So imagine that in the case where you are doing a lot of interaction with the AI models, as well as applications, right? Applications running, container applications running on top of the CPUs, alongside the GPUs. This gives much higher performance in terms of acceleration of networking. And on top of that, this is also being separate. This is an isolation technology, where VLANs and networkings and BGP routing all can be separated into different containers and different tenants. So that's one way to look at it, as in terms of performance. That's what we call accelerated computing. The second metrics we wanted to share is response, basically related to token response time. And we know that the token in AI, time to first token and token delays, latencies are key metrics in terms of delivering user experience. So we also measure that. We can clearly tell in a native pure software-based approach, the delays usually are at about 1 second per transaction. 1,000 millisecond, basically 1,000 per transaction, and then 250 milliseconds for the eBPF. eBPF is the industry's most efficient technology for leveraging kernel level acceleration, right? So that 250 millisecond is the delay you will get out of this stack. And then with the BNK, we could easily drive it down to about 30 milliseconds. For token-based, it's critical to get the fast response, to get to the first response of the token calculation. And then the last thing we wanted to show is, obviously, compute is accelerated. Now network can be accelerated. What actually, as an added benefit, is that CPU consumption with different stacks can be driven down to almost minimum, right? The whole CPU, because native stack will take up the CPU resource almost all the time. With an accelerated eBPF, it's optimized, but it's still dependent on CPU, right? And the last thing is the DPU acceleration, which takes away the pressure on CPUs completely. And these are the things that the performance metrics of these latency, transaction per second, and CPU consumption optimization, they are all relevant to the networking stack. They're not a heavy component of our open source tool chains, not our open source projects. And we can still use different automation tools, operation telemetry stacks to manage this. And so this is what we see as a way to combine accelerated computing with open source tools and use an accelerated networking to deliver AI services at host scale. And so this, I leave you here with a simple slide about this technology, what we call, we're kind of in partnership with NVIDIA to provide this. They are providing the GPU component. Most of the GPU servers would have this component. And we're providing the software on top to accelerate the networking, to provide security, and to give good observability at a network level into the whole-scale AI infrastructure. And I give you this last piece. And what we're trying to solve is not east-west networking issue. East-west leaves is a thing that only LLM trainers, corporations would need to run. What we're trying to focus is the north-south side of the traffic, make sure security is compliant, delivery of AI application is efficient, and make sure this is reliable for an AI application infrastructure. And with that, I have all of the information I wanted to share with the team. And any questions? Anything I can help address? I hope this can provide a different angle to the open source community. I know that we're talking about some proprietary or closed source component, but this component is closely integrated with open source platforms, Kubernetes and OpenStack. So we're open to any kind of a question, any kind of a integration option. Yes?
Hello. Hello. What exactly did you do in your F5 BNK?
So
Can
basically,
you explain
as
how-
I mentioned, there are two
what-
things, right? There's traffic management. Number one is traffic management in and out of the host scale AI infrastructure. So that's one thing. The second thing is the security. Basically, to isolate the tenant infrastructure host scale from other users in the same infrastructure, because now we're talking about delivering AI inference on a shared infrastructure, to many different users. So networking level isolation as a security measure. Yeah. Thank you.